An archer fires an arrow at 45 degrees. It's a 0.2 kilogram arrow, and it is observed to have reached its peak at 60 meters and then begins to come back down. If the archer pulled the string back only 0.3 meters before releasing, what is the spring constant K of the bow? Assume friction and other forces are negligible, so we don't have to worry about air resistance and all that good stuff. In this relationship, we're going to see that this arrow is fired off with some kind of energy, and it's launched into the air, and it's given enough energy in the Y component to launch it up to 60 meters and then come back down, and it's launched with enough energy to carry it in the X direction this far before reaching the ground. Because it's a 45-degree angle, we know that half of this energy is being shot up and half of this energy is being shot out. We know that because of our triangles. If we look at a 45-degree triangle and we know our trig values for that, we know that the X component's going to be 1, the Y component's going to be 1, and the component for the hypotenuse is going to be square root of 2. But we know that both the Y and the X components in this scenario are going to both be the same value. So, we have to use this relationship that says that the potential energy of gravity where the arrow has reached its peak is going to be equal to the kinetic energy of the arrow immediately after moving out of the bow, and that is going to be equal to the potential energy of the bow right before releasing the arrow. The potential energy of gravity at this peak where the arrow has stopped and reached a point where it begins changing direction in the Y components is going to be equal to the mass times the gravity constant times h. So we have 0.2 kilogram arrow times 9.8 meters per second squared, the constant for gravity, times the height, which is 60 meters. And it's going to give us 118 joules. So because we know that the potential energy for gravity is equal to kinetic energy, we know that our kinetic energy is 118 joules. Going further, because we know that our kinetic energy is equal to our potential energy of the bow, then our potential energy of the bow is also 118 joules. So if our potential energy of our bow is equal to 1/2 times the spring constant times the stretch squared, then if we solve for our constant K, while we know that our stretch is 0.3 meters, squared is 0.9 meters squared, we can find that our constant K is 118 joules times 2 divided by our stretch squared, which is 0.9 meters squared. So we find our spring constant K to be equal to 262 newtons per meter. Nonetheless, this energy that we're observing in this scenario is only 1/2 of the energy being exerted out of the bow. Recall that the bow is shot at a 45-degree angle, so half of that energy is going in the X direction, half of that energy is going in the Y direction. We accounted for the energy in the Y direction, but we didn't account for the energy in the X direction. So we found the spring constant K of our bow in the Y direction, and if we want to find the actual spring constant K for our bow that's traveling in the 45-degree angle direction, if we multiply that constant K by the square root of 2, we'll get our magnitude value of 370 newtons per meter as our spring constant K of our bow. So that is the constant K of the stretchiness of our bow, slinging the arrow into the air.